Now with molecular geometry, this was what we were hinting towards with VSEPR theory. We will shift ourselves to just look at steric numbers or electron domains. We can also call them electron groups, depending on where you took your general chemistry. That's what we're talking about. Things around the central atom is like what I like to call them. Now, VSEPR theory is when we talked about electrons repel each other. Electrons repel other electrons. So electron groups or electron domains repel other electron groups. So when we think about that central atom having multiple things attached to it, multiple bonds or lone pairs, those things need to be spaced out and given their own room. We can't shove them all into corner. Nobody shoves baby into the corner. When you think about those groups, you want to make sure that they are not repelling each other and adding to the repulsion energy, which is the bad type of energy. So here are 3 different molecules, all with 4 electron groups. Let's just remember that idea that a sigma bond is an electron group, a lone pair is an electron group. So all of these have a steric number of 4, whether they're sigma or lone pairs. They all add up to 4. They would all be sp3 hybridized then. If a steric number is 4, you take the S, the P, and the P. You homogenize them together and you make sp3. If your steric number is 3, so for instance, let's look at BH3, right? Or we can think about this Lewis structure that we just did earlier in the week, CH2O. You take the S, the P, and the P, and you homogenize them together to make sp2. Physically 3 groups around there. Now what happened to that extra P? It's the pi bond right there. Pi and a sigma. Together that is 1 group, right? Now if the steric number is 2, think about carbon dioxide. We only have 2 electron groups. We only need 2 atomic orbitals. sp hybridized for that central atom. So when we think about our geometries and our organization of all of these, hybridization is attached to the steric number. Also what's attached to that is the idea of bond angles, right? And tetrahedral electron geometries. Now a tetrahedral molecular geometry, such as methane, is when where all 4 electron groups are sigma bonds. If we think about nitrogen and ammonia, NH3, with the 1 lone pair, this is a tetrahedral, but notice how the bond angle is a little bit smaller. Once we institute a lone pair, we get a different type of molecular geometry. This was trigonal pyramidal. It's important to remember that because the bond angle was less than 109.5. Less than 109.5, 107, please remember one of those. It's important to note that the lone pair takes up more room than a bond, gives those lone pairs more space. Oxygen and water is even more of a depressed bond angle. This is what we called the bent molecular geometry. Important to note all of those. Less than 109.5 or 105 is also good to note. The other ones that we want to remember, BH3 or BF3, when we had 3 bonding pairs, that was the trigonal planar. And if we have 2 electron groups, such as CO2, or this example from your table 1.3, BEH2, linear, right? Trigonal planar has a 120-degree bond angle. Linear has a 180-degree bond angle. We'll get to those right now. Steric number of 3, trigonal planar, sp2 hybridized. All of these go together. So when we are looking at the steric number, we get a lot of information from it. So be well aware of counting the things around that central atom. And we realize that boron Has no formal charge here. Remember, he's the incomplete octet. He is sp2 hybridized because of those 3 groups around him. He still has an unhybridized p orbital, but it is empty on boron. Very important to remember. That p orbital is still there. Could be filled and be a pi bond, but for Bf3, it's unfilled and it's empty. When the steric number is 2, we remember linear. BeH2 is a good example. Carbon dioxide is one that we did too, so I'll redraw him here. Right. The p orbitals on carbon are being used. How can we tell? There's pi bonds. BeH2 has no pi bonds, so Be has empty p orbitals. Carbon is filled, we see the pi bonds. We'll be able to make those distinctions once we start getting more examples. So this chart is a great one to remember. We do need to know our molecular geometries. We'll practice them a lot, but notice how we only go to a steric number of 4. We don't care about 5 and 6 as we did in general chemistry. We're going to stick with these ones. Now, we talked about polar bonds. Let's talk about what that means in a molecule. Electronegativity differences result in polar bonds. Now, induction is the ability of shifting electrons within an orbital, and within a molecule, we can create something called a dipole moment. We will not be actually measuring any dipole moments or being able to report any dipole moments. All we really want to get out of this chapter is the idea of, is there a dipole moment, yes or no? Do I have a polar bond, and is the molecule asymmetric? So when we look at molecules with multiple polar bonds, what we really want to be able to say is, can we take the vector sum? Woo. So looking at this first molecule right here, chlorine to carbon is a polar bond, where the chlorines are delta minus and the carbon is delta plus. What does that mean of the overall molecule? Well, it's a vector sum. That overall, the polarity of the negative charge is in between the carbon or the chlorines, and the carbon still has that delta plus. Same thing with NH3. We have individual polar bonds resulting in a bunch of delta pluses on our hydrogens and a delta negative on the nitrogen. So overall, the polarity of this molecule points upward towards the nitrogen. Water has polar bonds. The overall polarity, the vector sum for that molecule points towards the oxygen, right? There is a net dipole moment in all of these molecules. Now, you have to know the molecule's geometry before analyzing the polarity, right? If you have not drawn the molecule with its proper geometry, you might actually assess it wrong. You might take the vector sum and forget what the actual molecule looks like. So for instance, if you just did water looking like this and you said it was linear, you might say that the vector sum would be net 0 because you forgot there's lone pairs and you forgot that that is bent, not linear. So be very, very careful when analyzing all of these. You have to understand and really value the overall idea of the geometry first before analyzing the polarity. We will be looking at electrostatic potential maps in class in a lot of examples. They look very colorful and very beautiful. The delta negative is usually the reddish color. The delta positive is more blue, purple. And what this just is our way of being able to visualize the electron density shift. Electrons reside with atoms that are more electronegative. And there is a deficiency with those electropositive atoms, things like carbons and hydrogens. Just a couple of polarity and dipoles that we can see. here, these all have dipole moments. Ones to make sure you realize is that even though in the Lewis structure we would draw things like oxygens to carbons as linear here, remember this is bent. Geometry is important, right? Things like pentane, carbons to hydrogens, nonpolar, no net dipole moment. CCl4, yes, carbon to chlorine is a polar bond, but what is happening here is the overall vector sum is 0 because every chlorine is pulling the exact same way. I want to just present another one. Carbon to oxygen is usually polar, but in carbon dioxide, we have an overall 0 dipole. Dipole moment is 0 because of the equal symmetry within that molecule. Intermolecular forces we should have seen in the second semester of general chemistry, sometimes in the first, depending on where you look, but typically in the second semester. So this might be newer thoughts, maybe fresh in your mind. Solubility, boiling point, density, state of matter, things like that, they're all affected by the attractions of separate molecules. Now, thinking about intermolecular forces between two molecules, at least two. You can't just draw one molecule and try to find the intermolecular force. It's not going to happen. So thinking about the three, I've ranked them here from least pull to most pull. Dispersion forces, everything has London dispersion forces. They're fleeting, they're temporary dipole moments. Dipole-dipole interactions, permanent dipoles, these are relatively strong. And we'll see when they exist in a polar molecule interacting with another polar molecule. Hydrogen bonding, the strongest intermolecular force for a pure substance. Hydrogen bonding is a special or a super dipole. Now, if two molecules are nonpolar, they still do have attractive forces. This is where we get London dispersion forces. Everything has London dispersion forces. Nonpolar molecules normally have their electrons spread out evenly around the nuclei, balancing the charges, so we don't usually have delta pluses and delta minuses. However, the electrons are in constant random motion within their molecular orbitals. So we can induce a dipole. Look at these electrostatic potential maps. Delta minus can be induced when it gets close to something that is delta plus or has electrons. What will happen is we will induce a dipole. It is temporary, it is fleeting, it is not permanent in any way, shape, or form. These two molecules come together and say, oh, hey, I'm attracted. Okay, I'm gone. And it's done. They're very weak. And so every molecule will have these type of induced dipole moments. And these are called London dispersion forces when those two things attract. Opposites attract. So there is a little bit of attraction here, but it's nothing to write home about. When we think about these fleeting interactions, they are generally weak. If there's enough of them, they can add up to be significant. And we'll talk about that in a little bit. So the greater the surface area of the molecule, the more temporary dipoles are possible. So looking at some real life example, the feet of a gecko. They have many flexible hairs on their feet that maximize the surface contact. And so geckos can walk up the wall. They're using London dispersion forces to walk up the wall. They're interacting with the surface of the wall, whether it's a window or concrete or wood. They're interacting and sticking slightly because of the increased amount of surface area, a lot of flexible hairs that maximize that surface contact. And so they can add up. Really, really cool type of example there. So when we look at something in chemistry, we don't really map out the gecko's foot, but what we can see is as we increase the number of carbons, we actually are increasing the number of London dispersion forces. So if we see 4 carbons to 5 carbons to 6 carbons, hexane, 6 carbons, has more London dispersion forces, and it's holding those molecules in the liquid longer. Pentane has a little bit less London dispersion, less surface area, so it's a lower boiling point. Butane, smaller molecule, less surface area, less London dispersion forces, lower boiling point. Remember, London dispersion forces and all intermolecular forces occur in the liquid phase. Therefore, the molecule that has the most intermolecular forces wants to stay in the liquid phase longer. So higher intermolecular forces result in higher boiling points. Now, more branching in a molecule lowers its surface area. Think about the difference between we can think about a rectangle versus a circle. The actual rectangle is more surface than the circle. Circles are the least amount of surface area for the sphere. So the more branching, the more spherical. Notice that this central carbon is not really seen on the outside anymore. And so it truly is less surface area there. And so longer surface area, more intermolecular forces. And I'm just going to abbreviate that IMFs. These are London dispersion forces, simply because we're only dealing with hydrocarbons right now. But notice how our boiling point decreases to the less surface area. Less intermolecular forces, not as many things holding those molecules together in the liquid phase. Now, dipole-dipole attractions are permanent dipoles. It is a result when a polar molecule lines up with another polar molecule with the opposite charge, the delta minus to the delta plus, delta minus to the delta plus. There is the intermolecular force. That attraction between one molecule's delta minus and the other molecule's delta plus that is permanent in the molecule is a dipole-dipole interaction. These are stronger than the London dispersion forces, and so they have to be taken a little bit more seriously. When we think about a molecule like isobutylene that is not polar, it has a boiling point of negative 6.9. Acetone institutes that polar bond of carbon to oxygen. We see an actual delta minus and a delta plus. Permanent dipole, so therefore dipole-dipole interactions happen within a solution of acetone. Boiling point drastically increases. Notice the two similar surface areas and structures. So comparing apples to apples, not apples to kiwis. We'll get to the weird stuff in class. Hydrogen bonding are exceptionally strong. These are still intermolecular forces. They are not a type of bond like a covalent or an ionic bond. They are not as strong as a covalent or an ionic bond, but they are very strong attractive forces between molecules. So thinking about things that have a hydrogen bonded to an electronegative atom, small electronegative atom, oxygen, nitrogen, and fluorine, and its attraction to a lone pair on another electronegative atom, oxygen, nitrogen, or fluorine. So here is that polar bond, delta plus of hydrogen, delta minus of oxygen. The hydrogen bond exists right here. There's the H bond. When the hydrogen of one is attracted to the oxygen of the other. Notice this right here is not a hydrogen bond. That is a covalent bond. That is one piece of the puzzle to the intermolecular force, hydrogen bonding, but it is not the only piece. It signifies that there is a super dipole, but it needs a lone pair of an oxygen, nitrogen, or fluorine to go with it. All right, another one. Delta minus on nitrogen, delta plus on hydrogen. Attracted to the lone pair of another. There is the H bond. Excellent. Wonderful. Now, only when a hydrogen shares electrons with a highly electronegative atom will it carry a large partial positive charge. And that large partial positive charge can attract the large delta negative charge on another molecule. So again, there it is. This one's the delta minus over here. There's the hydrogen bond. Even with these large partial charges, hydrogen bonds are still about 20 times weaker than a covalent bond. That should be a huge indication that they're not a true type of bond, just an intermolecular force. Excellent. Now, hydrogen bonding solvents can start to engage in hydrogen bonding if they are polar protic solvents. They have a polar proton. Hydrogen is a common term for a proton because if we think about hydrogen's nucleus, it has one proton, no neutrons. So therefore, a common term for hydrogen is a proton. A polar protic solvent we will use once we get into chapter 7. We'll use it a lot, and that will be really awesome. Now, if we again think about increasing the amount or the extent of the hydrogen bonding, we can start to see different boiling points. So trimethylamine, this guy right here, does not have hydrogen bonding. He has London dispersion forces, and he has dipole-dipole interactions. Ethylmethylamine has one hydrogen there attached to the nitrogen, so he does have all three types all the way up to H bonding. Very, very strong intermolecular forces there. So notice how his boiling point has increased from 3.5 for trimethylamine to 37 for ethylmethylamine. Now propylamine, 2 hydrogens. Lots of hydrogen bonding capabilities there. Yes, we still have London dispersion forces and dipole-dipole interactions, but notice how propylamine has the highest boiling point, strongest intermolecular forces out of these 3 because it has 2 areas to hydrogen bond versus just 1. Now, hydrogen bonds are common in things like DNA because they are what form the double helix, and some proteins to fold in an alpha helix. So thinking about hydrogen bonds, they are very prevalent in biochemistry and biology. For us, we're going to be looking at them in terms of solvent to solute interactions, similar to what you saw in general chemistry. And solubility. Like dissolving like. Hopefully we learned that in general chemistry, that polar compounds mix well with other polar compounds. If you have hydrogen bonding, you like to mix with other things that can hydrogen bond. Non-polar compounds don't tend to mix well with polar compounds. They tend to mix well with other non-polar things. So like dissolving like intermolecular forces dissolve like intermolecular forces. And so we know it would be difficult to get a polar compound like water to mix with a non-polar compound like oil. So we can't just wash our clothes in just plain old water. We need soap, which has both polar groups and non-polar groups. So we can start to see how molecules that are big and huge might have polar portions and non-polar portions. So that's how we can start to look at molecules within this class, and within the context, we can start to identify a polar portion or a non-polar portion. And the overall molecule, yes, we can establish if it's polar or non-polar, but it's really important to start breaking apart that molecule into its groups. That's something that we're going to start doing a lot of in this class. When given a molecule, break it apart, see what pieces it has. Identify, yeah, there's a formal charge there. Yes, this is polar over here. There's delta minuses and delta pluses. This is non-polar, right? So start annotating things a lot more. Be comfortable with whittling down things that you might be able to see to help you think about reactivity. And we know soap forms micelles in water, which help carry away the dirt and be able to, get things clean with water. Thank you so much for joining me.